Alrighty, so let's start the poster Sparker presentation, and probably you know the order, uh, to say Sophia first, Andy second, then Paweł, Olivia, and then Kia. Very good. Let me start the. Yeah, I'll be displaying them. Okay, so go ahead.
Okay, hi everyone. I'm Sophia. I'm working with Professor Schepenchik this summer on the prompt convection region of gravitational waves from core collapse supernovae. And it's been brought up a few times in previous talks, but just as a refresher, prompt convection makes the first stochastic feature of the gravitational wave signal, and it reverses these negative entropy and lepton gradients that are formed from the shock wave from neutrino losses and deleptonization at the core. It flattens these gradients during about 5 to 20 milliseconds after core bounce, but the quasi-periodic signal it emits continues for about 100 milliseconds after core bounce. So the goal of my project was just to determine the characteristics of this prompt convection signal in these gravitational waves, and we did that by injecting simulated waveforms into real noise with coherent wave burst. And you can see on the left some of these reconstructed signals where the blue region is what we define to be the prompt convection region. And you can also see some histograms of some different characteristics from this prompt convection region. We have the fractional HRSS, which basically tells you how much strength the prompt convection region has relative to the rest of the signal, and also the central frequency and central time. You can see they're pretty consistent across these different waveforms, with the exception of the more massive progenitor S25 from Radice 2019, which has a slightly wider distribution for the central quantities and a shifted distribution for the HRSS. And if you're a modeler or simulator, I've also included the microphysics of each of these simulations, if that is of interest to you. And I also tried a lot of different methods to try to determine the end of this prompt convection signal, which is pretty non-trivial. Two of the methods shown here on a noiseless waveform are just estimating this quiescent phase that comes after prompt convection as a polynomial minimum and seeing where the high frequency feature best fit line intersects 300 Hertz. And they both did a passable job. You can see each one with bootstrapped errors, but putting it in real noise is a challenge. And you'll also see a lot more about this in Paweł's presentation, which is coming up. And remaining questions are just, with these different characteristics of the gravitational wave signal, can we relate them to physical parameters of the protoneutron star?
Yeah, Andy.
Yeah, thank you for the organizer to provide this chance for me to give a talk about my research, and thank you for Merrick about for the invitations. Yeah, so basically what I'm working on is to search for core collapse, and I think the most reliable way is to do coherent based search, which is totally waveform agnostic, but this will have some of the LIGO data or the LVK data would only have single detector that is working on, and so it's not applicable to apply coherent searches. So basically, we try to use a machine learning to capture the shared morphologies of the core collapse and perform a search test. And to test on the robustness of our machine learning method, we include the tests that including like longevity test, which is we train on less than a quarter of data, and we prop the sensitivity across a month fit. And so this is the first plot here that you can see that we analyze across a full month of data. And we do see some of the performance drops, but by retraining and adding more information about the glitch characteristics, we are able to recover some of the sensitivities. And the other test is that like glitch resilience, we don't want our models to only learn on the core collapse informations. We also want it to be resilient to glitches, such as glitch overlappings with the core collapse signals. So here we also included like the legends here, which is glitches from different detectors, and we overlaps the core collapse on top of it. And we see that the general behavior is that our model is able to resilient glitch effects. And also, I think one of the things that people most cares about is the model overtraining to capture just certain templates of the core collapse. So we also have other tests that basically showing that our model is capable of capturing some of the general feature of the core collapse and maintaining similar sensitivities. But there's only one page for me to show my results, so some of them are on the poster. So please come to the poster, and so I can introduce more about the results. And also the most important part is the single detector performance. So then here we can see that for the dual detectors on all three real data, we can reach about 4 kilo per second of sensitivity. And so here, the black line here is the dual detector performance, and the green and the line here is its single detector kind of configuration. So it drops from 4 to 3 kilo per second, but the trade-off is that we are able to search for other duty cycles which a coherent-based method will not be able to work on. So if you're interested, click on to my posters. Thank you.
Paweł?
Right, so hello everyone. My name is Paweł. I'm an undergraduate here and currently writing my bachelor thesis under Marek. And my research area is into DLEDO time. And what I mean by that is that what is the time required in core collapse supernova process to emit a lot of gravitation, a lot of strong gravitational waves. And my first approach to the problem was by developing a dynamic threshold method, and this involves taking the envelope of the signal and some initial time interval, and we perform a search for the next value that exceeds 3 sigma of the initial window. If the next value doesn't exceed it, we elongate the interval and perform a search. And this at some point gives us the time of strong gravitational wave emission. And to actually verify that this method is working, I also plotted energy evolution for D15. And you can see that since the gravitational wave energy is proportional to the derivative of the strain, we capture the moment of strong energy release. But then I also turned to what Sophia said about prompt convection, about tracking the peak frequencies in the spectrogram and fitting a polynomial to the data. By finding the global minimum of such a polynomial, we see when the high frequency feature begin to dominate the spectrum. And actually, this also coincides more or less with my method. This is the result for S15 ASFHO. And when it comes to the reconstructed waveforms, the problem is that we are not likely to see the prompt convection. I mean, the global minimum method is not likely to be applicable. That's why what I did is I took the most energetic, the most powerful pixels in the spectrogram and then find the optimal fitting, which was either linear or square root fit, and then interpolate, just as Sophia did, to 300 Hertz, and then plotted my results. For more waveforms and other description, please visit my poster. Thank you.
Olivia?
Hello, my name is Olivia Korensky, and I worked with Dr. Marek Szczepanik and Alejandro Casillas-Lagos to study the high-frequency feature, how it's affected by LIGO noise, and how the high-frequency feature's slope can be used to test universal relations. So for the first part, I looked at, in order to test how this goes into LIGO noise affects this, what I did was I inserted 5 models, Meta Kappa 2023 being one of them, into over 600 different samples of LIGO noise using CWB, and it extracted the pixels that passed the SNR threshold. What I did was I used a chi-squared, modified chi-squared linear regression, so weighted by the strain to get the best fit, and then I plotted them on a distribution. Fortunately, most of the distribution were Gaussian, which makes sense because the noise is supposed to be stochastic. However, Kuroda's 2016 was not, which is not on here, but that's talk to me if you want to know why I think. When I compare the regular simulation, the raw simulation fit to the real noise fit, what I found was that the errors overlap somewhat significantly if you assume that for the distribution, the error is a standard deviation. Calculating the error for a bunch of slopes, which also have their own calculated error, is non-trivial, and that's something I'm still trying to figure out. But I do not think, for 4 of the 5 models, since the deviation was less than a sigma, I do not think it significantly hinders our ability to LIGO noise hinders our ability to calculate the slope of the high frequency feature. The second part, I looked at universal relations and I decided there isn't really an equation out there that directly relates the slope to universal relations, assuming that assuming that you have one mode, which using Alejandro's calculations, where the G1 mode, which is on the PNS surface, G2 mode, which is in where the Ledoux convection region is. Regardless of their names, they're related to the equations above, and I took the derivatives, did some systems of equations, and found out that you can get a pretty nice, elegant equation for both modes. What I did was I took the frequencies, plotted them for different models, and plotted them for different times, assuming that the high frequency start slope time is 0 seconds, and the frequency is 300 hertz. And what I think we can do, it shows a promising way, if we get real mass and radius over time data, we can plot the m dot over m, r dot over r relations against the predicted curves, assuming that one mode dominates, and we can see how well a first order aligns with the universal relations. Thank you.
Thank you so much. Thanks. Yeah, thanks. And now, Kia. It will not work.
That's okay.
I'm sure you
No worries. Hello, I'm Kai Schluterman, and this is just a blurb of some of the things going on in my poster. So sorry that it looks like that, but what I want to talk about is this new idea that we're doing, have been doing for about a year or two, of using distributional methods to look at a collection of different supernova signals all at once, instead of just looking at one star at a time, and seeing what we can detect from that. So in this top left, what I was going to point to is kind of a collection of signals that appear in one on-source window from a star that we see explode in the sky. We look at the loudest one usually and say that so far it has not been a supernova. And then what we want to do instead is something kind of like the picture below it, which is from a completely unrelated field, but it kind of demonstrates that we want to look at the shapes of these distributions instead. And so instead of looking at one point in that huge histogram, we want to say, if we have a histogram that's just background, and we have a histogram that has hopefully some gravitational waves in it, we maybe would see a bump appear. And that's really the whole idea of the project, is to look for a bump. The way we're doing that so far is this middle colorful plot, a diagram, where we have our so-called mother distribution of hundreds of years of background only data with no signal, and we split that up into two pieces, one of them continuing to have no gravitational waves, and then the other one we throw in our injections. Right now we're sampling from these three on the bottom, these three injections, just kind of as like a little landscape, but I imagine some people have opinions on that, and I would love to hear about that later after the fact. We then throw those two different distributions into our statistical test, our non-parametrical statistical test, and those, in theory, tell us if they are or are not the same distribution. And we expect, if one of them has gravitational waves, or enough of them, that they would trigger and say that our two sets are different. And in fact, it seems to do that. And this really small text you could see in the two plots there with our sample sizes, on the x-axis, you can't really read that, but on the x-axis we increase our number of injections, 0 injections being background. It's just our null case. We have a 5% false alarm probability. That's something that we tuned for, and then as we increase our number of injections, we get triggers. All of our tests across the board start to alarm more than 5%. Which is pretty exciting so far. That's all I have up here. What we're trying to do next is just decide kind of how holistically we want to continue this out, and say how many of these injection waveforms do we want to use, what kind of like spatial analysis do we want to do? Do we want it to correspond to where stars have been in our sky, and just how much more we can learn from this method? Yeah. That's about what I got. If you want to learn more, please find me in my poster tomorrow.
Yeah, thank you everybody for all these posters. So you are leading Jay to the discussion, right? And like 5 p.m.